Okay, so in this video, I wanted to show how you can compute the maximum um, average power transfer, okay, for an AC circuit. So the idea is as follows. First, well, we have the following circuit, okay, and we want to know what is the value of the impedance that we need to connect between terminals A and B in order to ensure a maximum average power transfer, okay? And we can compute the value of this impedance by computing the conjugate of the Thevenin impedance, okay? So the approach to solve this type of problems is to first compute the Thevenin equivalent, okay? In order to know what is the maximum average power transfer that can be delivered to the following load, okay? So the approach is to first compute the Thevenin equivalent between terminals A and B, and based on that, we can compute this load, okay? That ensures a maximum average power transfer, okay? And with that information, we can also compute what is that power, no? What is that maximum average power that can be transmitted or supplied to the load that is connected to this part of the circuit. So what we can do first is to compute that Thevenin equivalent. So first we compute the Thevenin voltage. So I will redraw the circuit as follows. First, we have here a voltage source, okay, with the following angle. Here we have a 4 ohm resistor. Here we have an 8 ohm resistor. And here we have the capacitor, okay? And here we need to write the value of the inductor, okay? And here we have the terminals of the circuit. So to compute the Thevenin equivalent, I will assume that there is nothing connected here in this part, okay? So I have an open circuit. And based on this information, I can compute the Thevenin voltage. And that can be computed as follows. I will assume that the current is flowing from the negative to the positive terminal, okay? And, well, we can apply this Kirchhoff, okay? This Kirchhoff current law, no, sorry, voltage law to this loop or to this mesh, okay? So here we have minus 10 with an angle of 0 degrees volts plus 4 ohms times I, okay? That this is the voltage drop of this element plus the voltage drop in this part, okay? Since here I am assuming that there is nothing connected here, there is an open circuit in this region, okay? So the voltage between these terminals, okay, let's label them as A and B, is equal to the Thevenin voltage, okay? Because there is no voltage drop in this element because I am assuming that there is an open circuit in this part, okay? So the current I, this one, will only flow through this direction, okay? So the voltage drop in these two elements will be equal to I times the impedance of these two elements minus J6 ohms, okay? And this is equal to 0. And if you input this into your calculator, you will have 0.7453 with an angle of 26.565 degrees amperes, okay? And well, you can see that the voltage drop of between terminals A and B is equal to the voltage drop of this impedance, okay, of these two elements. So we can compute this voltage drop between terminals A and B as I, okay, the current I, times the impedance of the 8 ohm and the capacitor. Okay, and this is the value of the voltage between terminals A and B. So if you plug in this value right here, you will notice that the voltage between terminals A and B, that is the Thevenin voltage, is equal to 7.4535 with an angle of minus 10.3048 degrees volts. Okay, this is the value of the Thevenin voltage. Okay, and now we need to compute the Thevenin impedance. Okay, so remember that to compute the Thevenin impedance, we need to switch off all of the sources in the circuit. So here we only have this voltage source, so we can switch off that element. Since here we have a voltage source, we need to replace that with a cable because we are assuming that the voltage source is off. Okay, so if you do that, you will have the following circuit. Okay, so we can simplify the circuit as follows. What we can do to do that? Okay, you can notice that this resistor is in parallel with these two elements. Okay, so the parallel between this 4 ohm resistor, um, okay, the parallel between this 4 ohm resistor and this impedance is equal to 1/1/4 plus 1/8 minus 60 ohms. And this is equal to um, 2.9814 with an angle of minus 10.3048 degrees ohms. Okay, so this is the value of the simplifying this 4 ohm resistor that is in parallel with these two. Okay, you can simplify these two because they are in series. Okay, that's why I am skipping this step, no, of simplifying these two elements because the simplification is directly because they are in series. Okay, and well, based on this, we can rewrite the circuit. Okay, and you place here an impedance A and B, and here we have the following 2.88 14 with an angle of minus 10.34 degrees, and these are ohms. Okay, and well, you can notice that this equivalent impedance is in series with this with the impedance of the inductor, and you will notice that the Thevenin impedance is equal to 5 ohms plus 2.9814 with an angle of minus 10.3048 degrees ohms. Okay, so this is equal to and the following value, that is 5.3437 degrees with an angle of 56.7064 degrees ohms. Okay, this is the value of the Thevenin impedance, and the impedance that ensures maximum average power transfer is the conjugate of the Thevenin impedance. Okay, that is equal to 2.93 minus 4.66 J ohms. Okay, so this is the value of the impedance that ensures a maximum average power transfer. Okay, and this will be the value of C sub L. Okay, so with this information, we can now compute what is the average, what is the maximum average power transfer that is given to this load. No, imagine that we have the following circuit. No, this is the Thevenin voltage. Okay, here we have the Thevenin impedance. Okay, here we have the terminals of the circuit, and here we have the impedance CL. Okay, so we can solve the circuit in order to compute what is the the average power of these elements. But instead of doing that, you can use the following expression. Okay, when you have an impedance, okay, in this part, in other words, you have a complex impedance, you can compute the maximum average power transfer by using the amplitude of the Thevenin voltage. You square that, okay? Well, you take the absolute value, you square that value, and then divide that by 8 times the real part of this impedance, that is this value, okay? That is the real part of the Thevenin resistor impedance. So if you substitute the Thevenin voltage, the magnitude of the Thevenin voltage, that is 7.4535, okay? And then you square that value and divide that by 8, and you take the real part of the Thevenin impedance, okay? That is 2.93, okay? So the maximum average power transfer is equal to 367 watts, okay? So this is the maximum average power transfer, okay? And this is the impedance that ensures that we are providing this power, okay? So you need to connect this impedance into these terminals in order to ensure that you can provide this maximum average power transfer, okay? So I think that we can make another example, but in this case, I wanted to show you what you can do in the case that you want to connect a purely resistive element. Okay. So in this case, what you can do, well, I think that it's better that we make an example. So here we have the voltage source that is 150 with an angle of 30 degrees volts. And here we have the 4 ohm resistor. Here we have the capacitor. And here we have an inductor. And here we have the terminals, okay? And we want to know what is the resistive element, okay? Here we are assuming that we want to connect a purely resistive element, not an impedance. In other words, we want to connect a resistor only. And we want to know what is the value of this resistor that ensures that the circuit can provide a maximum average power transfer, okay? So in order to do that, well, we know that the value of that resistor should be equal to the magnitude, okay, to the magnitude of the Thevenin impedance. Okay, you need to compute the magnitude of the Thevenin impedance to compute this purely resistive element that ensures a maximum average power transfer, okay? Given the circuit that we have. So what you can do is the following. First, well, we need to redraw the circuit in order to compute the voltage between terminals A and B. Okay, so I have redrawn the circuit, and the first step is to compute the Thevenin equivalent between terminals A and B. Okay, remember that the Thevenin voltage is equal to the voltage between terminals A and B. And what we can do is to say, okay, we have here a current that is flowing from the negative to the positive terminal. And you can apply the Kirchhoff voltage law to this loop. So we have minus 150 with an angle of 30 degrees volts plus 4 minus J 30 ohms times I plus I times J times 20 ohms, and this is equal to 0. So we have here that I is equal to 3.638 with an angle of 44.036 degrees amperes. Okay? And well, we know that the voltage between terminals A and B, remember that the current will flow into this direction. Okay? So here you will notice that, well, the voltage between terminals A and B is equal to the voltage of inductor, that is equal to I times the impedance of the inductor. And this is equal to 72.6606 with an angle of 134.036 degrees. Okay, and these are volts. Okay, so this is the Thevenin voltage. And now we need to compute the Thevenin impedance. Okay, so remember, to compute that Thevenin impedance, we need to switch off the current source. Okay, so I will switch that off. In order to denote that, we use a cable. Okay, and here we have a capacitor. And here we have the inductor. Okay, and well, you can observe that these two elements are in series. You can simplify that equivalent impedance. And you will notice that this equivalent impedance between these two elements is in parallel with this inductor. So we can say that 4 ohms minus J 30 ohms is in parallel with the impedance of the inductor, that is J times 20 ohms. And this is equal to 1 over 4 ohms minus J 30 ohms plus 1 over J 20 ohms. And this is equal to 9.4117 plus 22.3529 J ohms. Okay. Well, in fact, well, the parallel between these two is equal to the Thevenin impedance. Okay. Now, Remember that the resistor, okay, that we need to connect between these two terminals in order to ensure maximum average power transfer is the magnitude, okay, is equal to the magnitude of the Thevenin impedance, okay? So you can compute the magnitude of this value, and you will notice that this is equal to 24.2535 ohms, um, and this is equal to the resistor RL, okay? So the magnitude, okay, of this Thevenin impedance is the value that we need to, of the resistor that we need to connect between these two terminals in order to ensure maximum average power transfer. Okay, in this case, contrary to the previous example, we want to place here a purely resistive element. Okay, we don't want to connect a complex impedance. Okay, only we want to connect a resistor. Okay, in the previous case, we are assuming that we want to connect a resistor in series with an inductor or a capacitor. But in this case, we only want to connect a resistor. Okay, now we can write the Thevenin equivalent. Okay, so here we have the Thevenin voltage. Okay, and here we have the Thevenin impedance. Okay, and now we can connect between the two terminals of this Thevenin equivalent circuit the value of RL. Okay, and what else we can do? Well, one of the things that we can do is to compute the current. Okay, and the reason for that is that, well, when you have only a resistive element in this part, okay, a purely resistive element, you can use the following formula, okay, that is 1/2 times the magnitude of the current that passes through this resistor square times the value of RL, okay? So you can use this formula to directly compute the maximum average power transfer, considering that we only have a purely resistive element, okay? So what you can do is to substitute the values that we already have for this circuit. Okay. So remember that RL is equal to 24.2535 ohms. The value of the Thevenin impedance is 9.4117 plus 22.3529 J ohms. And here we have the value of the Thevenin voltage. That in this case is 72.7606 with an angle of 134.03 degrees volts. Okay, so this is the value of the Thevenin voltage, and here we have the direction of the current. Okay, so since this formula requires that we know the value of the current that flows through this resistor, we can apply the Kirchhoff voltage law to this loop. So since the current is flowing from the negative to the positive direction, we have minus 72.7606 with an angle of 134.03 degrees volts plus the value of the impedance, that is I, times 9.4117 plus 22.3529 J ohms plus I times the value of the resistor, that is 24.2535 ohms, and this is equal to 0. So if you solve this equation for I, you will have the following. You will have that I is equal to 1.853 degrees, and these are, well, the degrees are 100. 0.45, no, 4.45, 307 degrees amperes. Okay, so this is the value of the current, and we can use the amplitude of this current, or the magnitude, sorry, of this current. We can substitute this into this equation. So you will have that the maximum average power transfer is equal to 1 over 2 times the magnitude of the current, that is 1.80053. This is squared times, let me erase this, times the value of the resistor RL, that is 24.2535, and these are ohms, okay? So the maximum average power transfer is equal to 39.3142 watts, okay? So this is the result for this exercise, okay? So, but these are some examples in order for you to see how you can compute the average, well, the maximum average power transfer. The first thing that you need to consider is to compute the Thevenin equivalent. And once you have that, you can, for example, if you have, if you're connecting an impedance, okay, between the two terminals, well, you can use the following expression in order to compute what is the maximum average power transfer. Okay, well, when you have an impedance, no? In other words, you have a resistor in series with a capacitor or an inductor. Okay. But when you have or you're considering a purely resistive element, okay, remember that in order to know what is the value of this resistor that ensures maximum average power transfer, you need to compute the magnitude of the Thevenin impedance, okay? And well, in this case, you need to know, you can use the formula to compute what is the maximum average power transfer given the resistor that you have. And you can use this formula to compute that, okay? And based on this formula, you can know what is the maximum average power transfer in the case that you are only considering a purely resistive element, and that in this case is RL. Okay, so that's all for this video. I hope you like it, and see you later.